Okay, welcome to this third part of this video on support vector machines. So today we are going to look at a couple of more examples, primarily targeting something that is either nonlinear decision boundary or multi-class classification. Okay, we looked at this data set for logistic regression, where the decision boundary is kind of not linear, it is kind of circular. And we cannot apply as it is supported machine techniques so far that we have seen so far, because primarily we have been designing linear models with the supported machine. And that's the approach we know very well to come up with a maximum margin decision boundary and come up with a line that will divide that boundary either into class 1 or class -1. So we would like to use a similar approach for as many data sets as possible. But when you have a data set where the decision boundary as it is will look like a nonlinear decision boundary, we need to do some kind of transformation of the features on the data set, so that if you plot the transformed feature, it looks like there's a linear decision boundary separating the two classes. So that's kind of what you call the kernel trick. So I have a definition here. So the kernel is basically a function that is used to take the input data, the data as input, which data means the features basically as input, and transform them into some form that is more suitable for the processing that approach that we know. In this case, a linear decision boundary. So we are going to, we are given an actual coordinate system or the raw coordinate system that is having a nonlinear decision boundary, and we were going to pass them to a kernel function and get a transform coordinate system. And the transform coordinate system is going to have a linear decision boundary. And then we are going to use a regular approach of further normalizing it and then fitting support vector machine model. So that's the approach we're going to take here. And typically, the transformation, the kernel function we use is a polynomial kernel function. A polynomial means like x square, x cube, or even x1, x2. If you have x1, x2, you can do x1 square, x2 square. Also, you can try x1, x2. Depends on the shape of the nonlinear decision boundary that we're visualizing. Now here we do x1 square and x2 square for the simple reason that since the nonlinear decision boundary looks like a circle, so the equation of the circle looks like this: x1 square plus x2 square, which if x1 and x2 are the 2 dimensions, equals some radius r square. So we will try to find x1 square and x2 square for the given x1, x2, and fit that either as the raw x1 square, x2 square, or you can normalize it as well. As I said, normalization doesn't change the distribution of the data points. And we see that there is a linear decision boundary that is possible between x1 square and between the two classes. If you view it as x1 square and x2 square. So, so that's what we're going to do here first. We are going to take the x1, x2, the raw data set as it is, and then square them up, x1 square, x2 square, and the class assignment still remains the same. So to normalize, we find the mean and standard deviation, and then normalize x1 square, x2 square. So this is a visualization of the normalized system, the data set. And once we get into normalized coordinate system, and we have, if you look at the data points here, so these two looks like we can connect them with a straight line, and then you just take that parallel line and make it make it parallel to this red one. So that's how we choose the and the red one is this data point is more closer to the green data points, and these two green data points are the closer ones to the red data points. So we'll have 3 support vectors, 2 belonging to the green class, which is our -1 class, and so that's how we'll treat it. The inner data points, we'll call it as the green ones, class -1, and the outer data points, the red class, which is the class 1. You could change it, but once you fix the class assignment, you stay with what you have chosen. So the green ones are a class -1, and the red ones are class 1 in our case. So the three support vectors are given like this. The two normalized x1 square and x2 square values, and we add a 1 for the bias. So 2 class -1, the green data points, S1, S2, and then the red one, S3. And then we find the dot product table. And I think everyone is familiar with how to find the dot product. So for example, if you have to find S1 times S2, so both the terms here are negative and negative, so we can just use the values, and we use just the 4 decimals. If you need to round it, that's okay. Otherwise, you can just use the 4 decimals. And again, here the two values are minus, so the product will become positive. So 0.9111 times 0.7957 plus 1 times 1, which is this. Now, so that's 2.4333 for S1, S2. If you want S1 times S1, just then square the same value, 0.911 square plus 1. That will give you 2.4337. There's an online calculator as well. So if you, this is some website we are using for Gaussian elimination, but if you just pull this cursor down, you can see they have show all online calculators. And so they have a lot of online calculators. And if you just search for dot product, you'll get one. So there's an online calculator for dot product of 2 vectors. So what you can do is you can choose a number of other dimensions basically, and here we have 3, and we'll just form by coordinates. That's good enough, and just you can enter and see. Of course, you can use a calculator, but I think that will be using just typing the numbers in the calculator will be more quicker. But if you want to avoid any errors, we can use this. So you can, of course, you have to type the numbers here as well. So let us say you want to find S1 times S3 now. So negative 0.7769, and then negative 0.9111, and then 1. And S3 is our second vector. This is 0.2567. And then this is 0.1721, and that's a 1. So once you type the 2 vectors, you can click equal to, and that will give you the dot product, which is 0.6438 if you round it to the next decimal. That's what I have. S1, S3 is 0.6438. So you can use this dot product calculator as well if you want, instead of manually calculating it. Of course, you have to do for each term, S1, S2, S1, S3, all possible paths of product. So then we can fit this in our online Gaussian eliminator, which we had before here. So again, each row will correspond to an equation. So the first row will correspond to S1 class. So we have 2.4337 times A1 actually, plus 2.443 times A2 plus 0.6438 times A3. The class of S1 is -1. And then this is 2.4433 A1, 2.4880 A2, 0.6258 A3, and S2 is also -1 class. And then the third equation is going to be 0.643 times A1 plus 0.6258 times A2, 1.0995 times A3 equals 1. The class of S3 is 1. And then you can click solve the system. So we're going to get A1, A2, A3. Remember, you note down the sign of A1, A2, A3 carefully. And then W equals A1 S1 plus A2 S2 plus A3 S3. So that is your A1 here times the S1 vector plus A2 times the S2 vector plus A3 times S3 vector. So you have to do the term-wise multiplication here. So it's a minus and minus, so we just multiply the values. 1.7067 times 7.542. Then this is a minus and a plus, so we have to put a minus 0.9093 times 9252. And then both are plus here, so it's plus 1.3873 times 0.3316. So multiplying each of these A1, A2, A3 with the first term in this vectors will give you 0.9659. Similarly, now do the second term. So you have a minus here and a minus here. So it's going to be positive. So just multiply the values. 1.7067 times 1.0189. Now this is a minus and a plus. So we have to take that minus into consideration. Minus 0.8977 times 0.9252 plus 0.1191 times 1.3873. So that's 1.0736. Last term is all one. So it's just deal with the coefficient values. So it's it's a negative sign. So minus 1.7067 plus 0.9252 plus 1.3873. That's 0.6058. So that's what we have here. So that's your theta 1, theta 2, and B. So we can write down that if you need. So this is your W. So this is your theta 1, theta 2, this is your B. So the margin of the decision boundary right away is 2 divided by square root of theta 1 square plus theta 2 square, and then that comes out to be 1.4238. So it looks reasonably a very large decision boundary. And the equation of the line that will divide the decision maximum by the decision boundary equally will be W times X equals 0. So that is theta 1 X1 plus theta 2 X2 plus B equals to 0. So to get 2 points where this line will go through, so you put X1 equals 0, you get X2 equals negative 0.6058 divided by 1.0736, that will be negative 0.5643. And if you want to get the other point, so put X2 equals 0, then X1 will be equal to negative 0.6058 divided by 0.9059. That will be this number. So you can plot the 2 points along with the other normalized points and join those lines. We did it several times before. And that will be the line, this line. So you can now test with the rest of the data points in the normalized coordinate system with Wx, W times X. So for these two, we get very close to -1, even though it's not very exactly like minus negative, so minus 0.999 or -1, we get a little higher. That's okay because of the rounding in our calculations. That's the most likely reason we have it little higher than -1 or a little smaller than -1, I would say, because they are negative numbers. And then for the other data points, like for these two in class -1, we get it to be less than -1. And for this, again, for class 1, the support vector, we get close enough to 1. And the others are much greater than 1. And that's as expected. Because you see in the class 1, which is the red class here, the 3 data points are much farther away from the decision boundary. Whereas in the class -1, which is the green data points, these other 2 data points are much closer to the decision boundary Wx equals -1. So that's why you get these 2 values to be close to -1, whereas these 3 are much far greater than 1, because these 3 red data points are much away from this decision boundary Wx equals 1. Okay. So we can do some testing as well. So I have here some testing test cases. So this was our original raw training data that was given to us. We transformed that to x1 square, x2 square system, and then we normalized that as well and fit the support vector machine model and have a W times X here. So what we can do is if you're given some test data like 1.53.1, so if you go back to visualization here, so 1.5 is here and 3.1 is somewhere here. So this clearly lies in class 1, the red class. So let's see if we get that. So if you do x1 square, x2 square, these are the values, and then transform, normalize them using the same mean and standard deviation that we found for x1 square and x2 square. And let me see. And then is this as x1 square, x2 square, and the w here, w x1. Actually, this should be x1 square, but I know I should have put as x1 square because you're dealing with x1 square and x2 square. But let me make sure we do that. We're dealing with x1 square, x2 square in this data set here. So the data the coordinates are x1 square and x2 square. So so you see here we get 0.929, which is greater than 0. So that's all we have to see for testing. We don't need to really look for is Wx greater than 1 or less than -1. 0 is our cutoff. So like I mentioned here, this is our dividing decision boundary. So if W times X for a test case is greater than 0, it belongs to class 1. And if it is less than 0, it belongs to class -1. So that 1.5, 3.1, sorry, 3.1, -1.5 and 3.1. If you look at the normalized version, this is -0.53 and 0.53 almost. So -0.53 is somewhere here, and 0.53 is somewhere here. So it lies within that 0 to 1 range, the decision boundary. It lies within that margin. So that's why it is greater than 0 but less than 1 for W times X. Now, if you look at -0.9 and 3, which should be like -0.93 is also in the red class, class 1. So we get, so we square them and normalize, we get 0.335. And if you look at their normalized values is -0.8 and 0.4. So -0.8 is somewhere here and 0.4 is again somewhere here. So it's even much closer to Wx equal to 0. So that's why we get 0.33. Now, if you look at say -1, 2, -1, 2 is -1, 2 is kind of closer, because again, this is something I come up with as the circular decision boundary. It's not, it could be a little bigger. It depends on what the math gives us. So, but you see, -1, 2 is somewhat here, is here. So this data point is much closer to the class -1, the green data points, compared to anywhere outside. So it's more likely to predict it to be a class -1, belong to the green class, and that's what we see here. So if you do the math for -1, 2, it's 1 and 4 the square, and then get the normalized values and find the W times X. So it's not much less than -1. As I said, it's in the boundary. So it's like -0.45. So we say it is class -1. So if you look at where it is -0.77 and -0.33. So -0.77 is again somewhere here, and -0.33 is somewhere here. So it is in this negative class -1. Same thing with 2, 1. So if you go back and see where 2, 1 could be, so 2, 1 is somewhere here. And again, as I said, the circle is something I'm showing here. The actual decision boundary could be little different than this one. So again, this data point, the test data point, is relatively more closer to the green data points compared to the red ones. So it could also get classified as class -1, the green class. So let us see. So these are the normalized values, and we get W times X is -0.41725, and that's again less than 0, so it says class -1. So -0.18 and -0.79. So -0.18 is over here, -0.79 is over here. So that's in the negative side. W is less than 0. So that's how we can do testing with this. So you just transform first the test case feature values, also using the same kernel function, in this case, firing the feature values, and then use the normal and then normalize that test data using the mean and same mean and standard deviation as used for the training data set, and then you find the W times X. Okay. So this is about a non-linear data set. So let us now look at an example for multi-class classification. So here I have a data set where there are 3 classes now. So similar to logistic regression, support vector machine as it is not suitable for multi-class classification. It's primarily designed for binary classification. So if we have a data set that has more than 2 classes, we have to use an approach similar to what we did in logistic regression. So where we primarily try to fit multiple support vector machines, one for each class versus rest. So here we have 3 classes A, B, C. So you have to do a class A versus rest model, then a class B versus rest model, and a class C versus rest model. So that's what we'll be doing here. So this is a raw data set. Now we can normalize the entire data set right away and visualize that. So this is the normalized coordinate system. And so there are 3 classes, as I said. So these 4 data points belong to class A, these 3 belong to class B, the yellow ones, and then the blue ones belong to class C. So we need to fit 3 support vector machines, one for each class. So let us do first class A versus rest. So class A is again the one, the 4 data points below. So that's a class of interest. So we will color it red. So red class, we will use class 1 as a class assignment. And the data points belonging to class B and C will be coupled together. So everyone, the yellow and the blue data points will be coupled together as the rest. And that's like our other class, which is our green class. And we assign -1 to the to those data points as a class. So the first 4 are the class 1, the class A data points, and the other 7 are the class -1, class B and C rest data points. So we fit that. So the support vectors that need to be identified now. So if you look at this distribution, so these 2 green data points are more closer to the red ones, and this red data point is closer to the green ones. So we have 2 support vectors from green class and 1 support vector from red class. That's good enough to proceed. And if you join the 2 support vectors here, you get a line, and you extend that here, you basically have a decision boundary. Now, so use S1 from the red class, which is class 1, and S2, S3 from the -1 class, -1 class, and then go to the SVM math. You find the dot product table, and then use the kernel, Gaussian elimination to find A1, A2, A3. This is what we get. And then find the W vector, which is A1, X1 plus A2, S2 plus A3, S3. And you go through the math, you get this as a W vector. Now, so W is theta 1, theta 2, and B. Now, if you notice the value of theta 1 is kind of very small. It's like 0.00030 zeros followed by some numbers, 4. So for practical purposes, we can kind of discard that theta 1 term and simply use theta 2 and b. So the decision boundary can be simply as w times x is that negative 2.8030, theta 2 x2 plus b, and b is like negative 0.6364. So this can be our wx. And if you use that wx and find the wx value for all the data points here, we see the red ones, the class ones, we get much greater than 1 for the other data points. And for S1 that we use as the support vector, we get almost 1. And then for S2 and S3, we get negative 1. And for the other data points, we get less than negative 1. So these are all as expected. So now let us try to fit that decision boundary in the normalized coordinate system by setting w times x equals 0. And actually x1 is 0. So x2 is, if you set x1 is 0, but actually there's no x1 terms. So it's basically 2.80. Let me show that here. It's going to be negative 2.80. Increase the font size. It should be. So times x2 minus 0.6364 equals 0. You can actually divide by minus 1 on both sides. So this is plus 0.6364 equals 0. So x2 is going to be simply negative 0.6364 divided by 2.803, and that's that negative 0.227. So x2 equals negative 0.227 is kind of like a cutoff. And remember, this is our equation for wx. W times x equals 0. So if w times x is greater than, sorry, if we can set as equal to 1. So this is the decision boundary for class 1. And in this case, that's going to be this equals 1. It looks like, a straight line. It's just going to, so you see, this doesn't have an x1 term. So this line is going to be parallel to the x1 axis because it does not have an x1 term. So it's going to be parallel to the x1 axis. And if you plot it, actually, let's do that first. So this is x2 equals negative 0.227. This one. And the decision boundary that separates the two classes is basically this line. So this line everywhere, it is parallel to the x1 axis. So it doesn't have an x1 value. So it's only x2 equals negative 0.227 everywhere on this line. So it's going to be a line that just goes parallel to the x1 axis. So we can try to now get the equations for the wx equals 1. So this is a wx equals 1 line, and let us try to get this point where that line goes through. So if you do the math, it's 2.803 times x2 equals that 1 minus 0.6364, and that's going to be 3636. So x2 equal to that 0.3636 divided by 2.803. That's let me check if I did any mistake. Okay. See, this is where you became careful. We took this version. But remember, I used to say that you have to use the w times x as it is that we get. So this is our original w vector, right? So this is our original W times X, so we have to use that. So we could set that equal to 0 and then divide by -1, but so I made a mistake. So for W times X equals 1, we have to use this version equals 1. Okay, so that's our W times X. So, and then we can divide by -1 if you want to, but we have to use this version of the original version of W times X. Okay, so because that will make the math different now. So this equals 1 plus 0.6364. So that's going to be 1.6364. So x2 equals 1.6364 divided by -2.803. And that will give you around this 0.5 that we got. 1.6364 divided by 2.803 is -0.58. So x2 equals -0.58 is this point where this line will go through, wx equals 1. Now in the same discussion, so what we can do is, so for all these green, for all these red data points that are really in class 1, so anything belonging to class 1, wx will be greater than 1, right? So again, our w is x is this. We have to use original. So wx greater than 1. So we can play around this as well. So -2.803 times x2. I'm just taking this to the other side. So the greater than sign will still stay as it is. 1 plus 0.6364 is this. So now if you divide on both sides by negative number, we have to change the less than sign. So you say x2 is less than or equal to 1.6364 divided by -2.803. So when you divide by negative value on both sides of this inequality, the inequality changes to the other one. So it's greater than here, so it should be less than or equal to. So that means x2 less than or equal to -0.58 will be the region for wx greater than 1. That is our class 1. Okay, red class. So this is our negative number. So anything less than -0.58, 0.58 will be this class. So it makes really sense that we got less than or equal to -0.5, because equal to is that line, this line that goes through that point, and anything less than will be below that in this case, because it is negative side. So so x2 less than or equal to -0.58 belongs to class 1 in this case. Now for the positive, for the negative class, -1, so it will be w times x equals -1. We can right away go to this. So for this side, it's going to be wx less than or equal to -1, like we had here. Wx greater than or equal to 1. We can say this will be less than if you do that. So we could do that as well. Let me do. Let's do separate. So I wrote here for the red data points, these red data points, x2 is less than or equal to 0.58. So let's do first equals -1. So again, this is our wx equals -1. So -2.803 times x2 equals -1 plus 0.6364. That's going to be a 0.3636. So x2 equals 0.3636 divided by -2.803. That's going to be that -0.12. 13. So 0.13. So x2 equals -0.13 is this point, and the line goes through that data point. And for all these other green data points, x2 will be actually greater than. Well, I think I made a mistake here. Oh, okay, I'm sorry. -1 plus 0.6364 is negative. Okay. So -1 plus 0.6364 is negative 0.3636. So this should have been negative as well. So negative divided by negative is going to be a positive. So x2 equals 0.13. This is a positive value. Okay, so -1 plus 0.6364, take it to the other side, is negative 0.3636. So that divided by negative 2.803 is 0.13, a positive value. So 0.13 is this point. So x2 equals 0.13 really goes to that point. Now, for all the other green data points, x2 will be actually greater than 0.13, and we can check that. That's because for all the green data points, w times x, this is in class -1, so we wanted w times x to be less than -1, like we got here, less than -1 for the green data points. So again, this is our w times x less than -1. So negative 2.803 times x2. Let's be careful. So I'm going to take this to other side. So it's going to be less than -1 plus 0.364. So negative 2.803 times x2 is going to be less than negative 0.3636. So now you see here, we are going to divide both sides by, or divide this by negative value, 2.803. So that's going to be x2 greater than or equal to negative 0.3636 divided by negative 2.803. So that will make it 0.13. So x2 greater than 0.13 is going to be the value for the other green data points. Okay, so again, this is just for interest that we did all these details. The only thing that we need to remember for, because again, this is not the only problem, this is just class A versus rest. So the main thing that we need to remember here is this W times X for class A versus rest, the decision boundary for class A versus rest. Similarly, we have to find decision boundaries W times X for class B versus rest and class C versus rest. So that should be our focus. Okay, so for class B versus rest, again, going back to the original visualization, the yellow color data points are class B, and the other seven are class A and C, which is rest. So this is how they look like, the three red data points for class B and the other green ones, class A and C, are considered as rest here. So these two green data points are more closer to the red ones. So we could treat these two as the support vectors from the green class, and this one, the red data point, is a support vector from the red class. And that's going to be the margin of the decision boundary between the two classes if you go with these three support vectors, as I am showing here. Now, this looks like a little narrow margin. As well as if you look at this green data point here, it's kind of more closer to these red data points compared to the rest of this green data points, or even this class A data points over here. So if you want to look at any other option that is available, you can treat, as I said, this green data point to be like an outlier, and it should have been actually classified as class B instead of class A, but the data set given to us classifies this as class A, so we'll stay with that. But for building the class B versus rest model, we will treat it as an outlier, okay? So you don't worry about it, and try to fit a margin that looks like this. So using these two red data points as support vectors, draw a line that connects these two red data points, and then draw a parallel line as wide as possible to reach the green side. And you see you have this line that goes through this green data point. It doesn't exactly go through this one, so we could just treat this as a support vector because we already have two data points as support vectors of the red class. So we just use this one as a support vector of the green class. So these are our three support vectors now, the S1, S2 from the red class, which is class 1, and then the S3 from the green class -1, and then go through the math for that. As usual, the dot product table for support vectors and A1, A2, A3, then the weight vector A1, S1 plus A2, S2 plus A3, S3. So this is your W vector, theta 1, theta 2, and B. So here nothing is zero, so you have to use as it is. So W times X is going to be this. Negative 1.9791 plus 2.0995 x2 minus 0.3169. And you can find the margin of the decision boundary as using this theta 1 and theta 2 to be this. Now, this is kind of like a soft margin decision boundary here because we kind of came up with this decision boundary by letting this green data point to actually belong to class B. So if you compute the W times X values for all the data points here, you see here for S3, which is this green one, we get as expected close to -1. And for the other green data points, we get these two less than -1 as expected. But this green data point, which is like an outlier and pushed to the other side, we get the W times X value to be like 1.165. And it's not less than or equal to -1 for the reason that because we treated it as something that belongs to the red class. And for the red class, this is a decision boundary Wx equals 1. And anything above that will be Wx greater than 1 actually. And that's what we're seeing here for this green data point, which we are treating as an outlier belonging to the red class, we get Wx greater than 1. Okay, so that's justified. And then for these two red data points, S1, S2, we get Wx to be almost 1 as expected. And for this data point, we get 2.74755. That's because it's much away from the decision boundary, greater than 1. And then for the other green data points in this class C, rest class, these are also less than -1. And this is less than 0. That's good enough. We just want to be because you see here this is this data point over here, and it's very close to the decision boundary, so it's kind of -0.33121. So now if you went with the hard margin, so the other decision boundary that we had originally was this one. So here we don't have any outlier and we don't have any data point in the margin as well. So this is kind of the hard margin support vector machine we can call that doesn't have any outlier or any data point within the margin. So if you, but of course the margin is very smaller. So if you went through the math for W times X, we get this as W times X. And if you find the margin of the decision boundary using this theta 1 and theta 2 here, we get it to be 0.1132, which is much smaller than what we got here, 0.6932 that we had for the soft margin support vector machine. So this scenario or example kind of will illustrate the trade-off between soft margin and hard margin support vector machine. So by just allowing one data point to be like an outlier and building a soft margin support vector machine, we are able to build a more wider margin classifier, and that is more likely to be more accurate compared to this narrow hard margin support vector machine. So if that's why, again, visualization is the best tool that can help us to identify such presence of an outlier data point. If we just disregard it and go with a wider margin, we'll be able to build a more accurate classifier and more wider margin classifier. Now, again, by accuracy, what I mean is we shouldn't be focusing on the test data points, because the test data points with this hard margin support vector machine are much away from the decision boundaries other than these two cases. So for the data points as it is here, we are going to get less than -1 for all the -1 cases and greater than 1 for all the red class points. But if you have something outside of this training data set, if you bring in a test data point, again, we are not having a binary class situation here. We are having a class A, B, C, the three classes, and this is just one of the three support vector machines you're building. Class B, this is rest. So using this W times X may not be a good idea because we are having three classes here, and using a very narrow margin support vector machine for one of the three one of the three support vector machines may not be a good idea for the overall result. Okay, because it may lead to wrong prediction. The sense that, so for example, if I bring in let's do that. So if I bring in a data point here, which technically belongs to the red class, okay, it technically belongs to red class because it's more closer to the red data points. And but if I use this W times X, it's going to predict it to belong to the rest class and predict it in such a way that it actually belongs to class A. And you see here, this data point is not very close to any of the class A data points. These are the four class A data points here. It's much closer to the other three, these three class B data points. On the other hand, if I just use take this and go and then put it here, it belongs to class B. Okay, so that's the idea behind this using a wider margin as much as possible. And we're not letting any outlier. We're not we let one outlier, but we are not letting any data point within the margin. That's good. So we're just letting one data point to belong to class B as an outlier, but there's something else that's an outlier within the margin anywhere. So this is a reasonably good soft margin classifier, and it can cleverly identify boundary cases like this. Okay, so a test case where it should really belong to class B will be predicted to belong to class B in this case. Whereas if you use a very narrow hard margin classifier, it may wrongly predict it to belong to some other class. Okay. So let's do the class C versus rest. So these are the three of four class C data points. This should be class 1, and the rest as class rest. So there's a clear no support margin here. So we can treat S2, S3, these two as the green support vectors, and then this one parallel to that as the red support vector. And this should be a straightforward support vector machine calculation here. Okay. So go to SVM math for this, and we find W1 to W to be this data 1, data 2, and B. And the margin should be reasonably larger here as well, 0.6172. And you can go to the WX equal to 0 process to fit a line that will divide this margin, but we are not interested in that. We'll straight away go to the prediction. So we'll do the prediction, predict it on the given data set first, and then we'll predict it on any test data set. Okay, this is an important part of this multi-class classification. So we got the WX values for each, which I didn't write it on the top here. I could have written it, but there's no space. But it should be clear by now what WX values we use for each class. So for class A versus rest, this is the WX equation we are going to use for class A versus rest. Okay. Would reduce this a little bit and create space. Again, this approach is similar to what we did for logistic regression as well. There we had data X for each class. So this is the WX for class A. This is rest. We can do a similar thing for class B versus rest. And we'll use that soft margin class B. So this is class B, this is the rest. And then for class C, this is the rest. Yes. That's the equation here. So this is the equation. Okay. So what we need to do is take the normalized values for the coordinates for each data point, and this is the original class. So this is the actual class given. So we're going to see whether we are predicting to be the same class or actually different. Okay, so for each of these models, we are going to say W times X equals this. That's why I copied that, but it didn't get copied. Okay. All right, so we are going to, of course, for this class A is stressed, X1 is not needed, but so X plugging in X2, let me show that. We can do this in Excel. So 1.77325 negative times 2.803, which is also negative, minus 0.6364, we get 4.334. And then this W times X is based on this equation for class B, which is rest. And that's going to be negative, that is going to be negative 9791 times negative 1.5 times 1.53656 with the negative plus 2.0995 times x2, which is this 1.77325 with the negative minus 0.3169. So that's going to be 0.99 negative 0.999882. And then this one, which is by using x1, x2 here, we get this number. So among these three values, Wx values for this data point, we have to pick the larger one because remember we use red class as class 1. So anything, any Wx value greater than or equal to 1 is kind of what we are targeting for the data point that we're looking for. So we have to pick the largest of the Wx values and say that is the predicted class for the test data point. And that's going to be, in this case, class A, which is same as the actual class. So we can do that for all such data points. So in Excel, we can kind of automate this. So I have it somewhere here. Okay. So I have the actual, so this is actual coordinate and this is a normalized version. This should be little somewhere here. Okay, this one. All right, so the normalized version, and then so you can hard code just once the Wx value. So this is the Wx for class A, which is stress. This is the W times X for class B, which is stress. So you hard code the theta parameter values, but you make these as the variables. So this is going to be, for example, L89. This is column L, row number 89. So that's our X1. And M89 is going to be our X2. So make that as variables, L89, M89, but hard code the theta 1, theta 2, and hard code the theta 1, theta 2, and the B terms. Similarly here, hard code the theta 1 3.2212 times this L89 plus theta 2 is 0.3504 times M89, which is X2, plus the B, which is actually negative 1.1383. So that's hard coded theta 1, theta 2, and B. And once you do that for one, you can just copy and paste for the other data points. And for each case, we have to pick the larger one. So for the second data point over here, the largest among these three W times X values is this. So again, that's class A. And for third data point, the largest among these three WX values is this. So we go for this. Now for the problematic data point, which is that outlier thing, if you remember that we looked at before. So that is this data point over here. So that's basically, if you look at the original data set, that's as it is, that's this one, this guy. So even if you look at the original data set, it's more closer to the LO class, at least relatively, somewhat, compared to the other class A. Let's see what the model is predicting. So you're getting class A1, the class A is stressed, because there's no ambiguity there. For class A is stressed, this is clearly, this was used as a support vector, so that should be 1. Or greater than 1, that's fine. Now, class B viscous rest, it was used, treated as class B data point here. In class B viscous rest, it was considered on the class B side. And its W times X value was actually 1.16, as we saw before, slightly greater than 1. And then class C viscous rest, definitely it's not in class C, so we get WX less than -1. So among these three values for WX, we have to go for the larger one according to our convention, and the larger one is 1.1654, which really belongs to class B now. So that's why the SVM ultimately is categorizing this to be a class B data point compared to a class A data point according to the prediction. Again, this is a prediction, but the actual class is class A still. We can't change it. And for the other data points, all the predictions are as expected belonging to the actual class. Okay, so we can do a similar thing with the test cases. So just pick up some numbers which are not part of the training data set and go through the same process. And so for example, if I pick 1.8, 1.95, so 1.8, 1.95, again, okay, I use a normalized. We don't have visualization of the raw data set. This is a normalized version, negative 0.44 and negative 0.04. So negative 0.44, negative 0.04, negative 0.44, negative 0.04. Okay, that's kind of something like this. So let me make a different color so that there's no confusion. So this is a test data point. Now, so again, you see here, it's more closer to the red, it's more closer to the yellow class, which is class B, and not closer to this class A data points. So let us see what the prediction gives us. So the class A, okay, so here I have it the other way. So this is class C is stressed, then class B is stressed, then class A is stressed. So class A is stressed is less than -0. So we are looking for the greater one. So you want really something to be greater than 0 at least, preferably greater than 1, but at least greater than 0, because you're looking for the targeted class should be greater than 0. And even if you don't get greater than 0 for all the three WX values, you have to pick the largest among them. So in this case, largest among them is 0.4845 is greater than 0 as well. So it really definitely belongs to class B, as we see. Okay, so that should really go to class B rather than class A. So if you had used that narrow margin, hard margin, this classifier, it would have put it in class B. So class A, it would have put somewhere here, that data point, and that would have made it to belong. Because you see, this is this one here, negative 0.54. So that should really go here, right? So it will make it to belong to class A. And that's not correct. It's not really close to any of the class A data points. So you can visually analyze and see if the prediction is making sense. Okay, the predictions should make sense. That's why we go through all this math. But if they're very close somewhere, the math will dominate and tells things. Like you see here for this data point, 2.62 and 2.2 actually, and this is a normalized version, 0.24 and 0.24. We get all the three WX values to be negative. So among these three negative WX values, you have to pick the largest, and that's this one. And that's class C versus rest. So let's see, 0.24 and 0.24, if you go to the normalized system, 0.24 and 0.24 is actually this one, somewhere here. So it definitely does not belong to class A, but it could either belong to class B or class C. So that's where that ambiguity is. So if you plot it in this class C versus rest boundary, the 0.24, 0.24, it really falls here. So a little here. So it's kind of, or even here, it should be here, right? So if you divide this separator, we say it belongs to the rest, okay? But if you put it in the class B versus rest, that's here. So let me kind of to rename this in the slide. Remember, so class C versus rest, it puts in the rest, not in class C. So it puts in the rest. And let us see where this guy puts this. Did I have a copy of this? Yeah, so let me read that. So 0.24, 0.24 is this. So this also puts it in the rest category. It's not putting it in class B, which is a targeted class here, it's putting in the rest. So both the class B versus rest model and class C versus rest model are putting these data points in the rest category. So that's why they are both like negative. So the class C versus rest model is giving WX value less than 0, which means it's not putting it in class C, it's putting in the rest category. And the class B versus rest model is also putting it in like the rest category because it's also WX is also less than 0. So both models are putting it in the other category. Of course, this class A success will definitely put it in the rest category as well because it's not really belonging to class A. So all the three data points are putting it in the other rest category. So this is a clever case where to pick the best of the worst. So that's why we use we make use of the approach of picking the one with the largest WX value as usual to be applied here as well. So between these two negative numbers, the largest is this. So we'll go for that WX. That means it belongs to class C. Even though the class is the rest model is not predicting that to belong to class C, because if it has to belong to, if the model has to predict it to belong to class C, the WX value for it should be at least greater than 0. It's not greater than equal to 1. It should be at least greater than 0. It's not here. But none of the other models also putting coming up with that WX values to be greater than 0 as well. So you have to pick the largest among the negative WX values, in this case, that will make it to belong to class C. Okay, that's a good example. The last one is also a kind of such boundary point, 2.6 to 1.8. We didn't get a negative, but it's very close to 0. But again, this is technically greater than 0. So that is sufficient enough because these two are really negative. And this is the largest among the three WX values, and we make it to belong to class A. So multi-class classification is really going to be interesting. Because we need, especially when we use binary classification classifier like the logistic regression or support vector machine and come up with the WX or theta X values for each class and then become the actual class, the predicted class. based on the largest theta x or largest wx value, that will be really a smart decision to make. And things are very simple. In cases, we just pick the largest wx or largest theta x values among the three models. And if the wx value is greater than 0 and the largest, that's really a meaningful prediction. But or meaningful in the sense that really they are probably a good correct prediction. But if the wx values are all negative, then you have to just pick the best of the worst. And technically, in this case, for this one, it could be either B or C, because we are given a data set where we don't have a decision boundary. That's the problem. We have to come up with a decision boundary so that we can predict the class for any test data point. So that 0.24, 24 actually is plotted here. So it could belong to class B or it could belong to class C, but we give a toss up and make it belong to class C based on the math. So that's why, as I said before, ultimately the math will dominate and decide the class, because everything is based on the math here. So W times X will decide what's the predicted class for the data point. There's one more example I just want to show. This is multilinear modeling. And this actually can be applied for any linear classifier like logistic regression or support vector machine. The idea is, so if you're given a data set, the raw data set like the one shown on the left, if you try to visualize a decision boundary, it's kind of non-linear, definitely, between the red class and the green class. And even if you apply the kernel trick of squaring x1 square, x2 square, or doing x1, x2, I tried it. It's not going to give you a linear decision boundary in the transform data set. You could try this one. I just tried for curiosity. Let me see where it is. Yeah. Let's see. I was trying this just now. Okay, here. What I just tried is, again, use the kernel trick approach. So this is x1 square, and this is x2 square and x3, x1, x2. So these are both all like product, either x1 times x1 or x2 times x2 or x1 times x2. So all the product kernel trick, the same kernel trick is applied here. So I used, this made me remember the refractive index data set that we had, and we had 4 features. So here we have 5 features. And again, these are the classes. So the original x1, x2 was this. Okay, this is the original x1, x2, the blue class and red class. And so the blue class is treated as 1 and red class is 0. So I fitted this with the logistic regression online classifier that we use for logistic regression, and we got that data X. So I kind of deleted that, I believe, or I have it here, but I think I don't have that data anymore. But use this one, which used before, and use 1 and 0 for the classes, and enter all the 5 features. We get a W times X. So since 5 features are there, we're going to get 5 theta parameters: theta 0, theta 1, theta 2, theta 3, theta 4, and theta 5. So theta 0 is more like the B. So in addition to that, we're going to get 5 theta values. So multiply that with this feature values, you're going to get this theta X. And for class 1, they're all greater than 0, much greater than 0. And for class 0, they're all less negative, much less than 0. So that's a correct prediction. They are not very small values less than 0 or very small values greater than 0. They are reasonably much larger. So that seems to be a good fit. So We can try with 5 features like this. Basically, we want a product thing, either the feature square itself or x1 times x2, and use all the 3 additional cases as part of the feature set and build a model. That's one way. It may or may not work, like it was working here, it may not work in some other data set. The other approach, which I really want to highlight here, is if you visualize this data set, it's more like a parabola that is separating the 2 classes. So a parabola is something like it will keep reducing like this and then pick up the boundary, So can we make it more like a linear like this? So it reduces and then increases. So we have to see where that bottom is. And the bottom really is like in the x1, it keeps reducing the x1 values. And when it reaches, say, 5, actually it's like 4 point something, but we can use this data point here that has x1 as 5 as a cutoff. So we really don't want to go up to 5 because, as you see here, the bottom is reached less than 5. So we can use x1 less than 5 as a cutoff and x1 greater than equal to 5 as the other cutoff. So that means all the data points with x1 less than 5 will belong to this group, and then x1 greater than equal to 5 will belong to this group. And for each of these sub data sets, we can find a linear decision boundary that separates the 2 classes. For this one, we can find a linear decision boundary. So we can actually split a given data set into 2 sub data sets like this. If each of them are having a linear decision boundary like this, whereas the original does not have a linear decision boundary, whatever you try, and even the kernel trick may not work, then it is okay to split the data set into 2 sub data sets. And for the testing, the test data point will belong to one of these 2 data sets. So depending on what the x1 value of the test data point is. So if it has an x1 value less than 5, you use this classifier to classify the test data point either to red class or green class. If it is greater than or equal to 5, use this classifier to classify to either the red class or green class. Again, here we have only 2 classes. So it's not a binary, it's not a multi-class classification, it's just binary classification. But we don't have one model to do the classification. We are building 2 models to build the classification. That's the idea here. We could extend it to multiple models, multiple classes as well. So not multiple classes, multiple models as well. So if your data is more like a wavy thing, then we could use this approach to build multiple linear classifiers for the different sub data sets. And depending which of the data sets the test data point will fall, then you just test with that classifier. Okay, so with that we stop.